From the blender on your kitchen counter to the massive, city-sized machinery in factories, electric motors are literally the invisible workhorses of our world. They are absolutely everywhere. But have you ever actually stopped to think about how they work? How do you turn a jolt of electricity into smooth, powerful motion? Let's dig in.
Okay, so at the very heart of the most common electric motor, what's called the induction motor, is a trick that honestly feels like straight-up magic. The part in the middle that spins, it's not physically connected to anything that pushes it. There are no wires feeding it power directly. So how on earth do you make it spin?
And the answer is just so elegant, it's brilliant. You do it with an invisible, untouchable, but incredibly powerful rotating force field. And we're about to see exactly how this amazing trick is done. All right, to understand the trick, you first have to meet our two main performers. Every single one of these induction motors is basically made of just two fundamental parts. You've got the stator and you've got the rotor. So the stator, that's the stationary outer housing. You can think of it as the stage for our show. And the rotor is the performer that sits right inside. It's the part that actually spins and does all the work. The most common type, which you see here, looks like a cage, which is exactly why its nickname is the squirrel cage rotor. So let's take a closer look at the stator. Now, it's not just some simple metal ring. It's actually built from a stack of really thin, insulated steel plates, which helps cut down on energy loss. And tucked inside of these beautiful copper wire coils, all arranged in 3 separate sets, or what we call phases. This is where the electricity from the wall actually comes in. And here is the star of our show, the rotor. This is that squirrel cage design we were talking about, and you can see why. It really does look a bit like a hamster wheel. It's just a bunch of conductive bars, usually copper or aluminum, all connected by rings on both ends. And here's the absolute key. Notice there are no wires, no batteries, no direct connection to power whatsoever. It just sits there.
So, if the rotor isn't wired up, what in the world makes it move? Well, this is where we get to the real secret sauce of this whole thing, the creation of what's called a rotating magnetic field. The secret all starts with the power supply. The stator gets fed 3 separate alternating currents. You can see them here as 3 distinct waves. But look, they're perfectly out of sync with each other. Each one hits its peak at a slightly different moment. This staggered timing, well, it's the key to absolutely everything. And here's where the magic happens. Each of those 3 currents going into the coils creates its own little magnetic field. But because the currents are out of sync and the coils are arranged in a circle, something amazing happens. They don't just add up randomly. Nope. They merge together to create one single unified magnetic field that has a constant strength, but, and here's the cool part, its direction actually spins. Okay, let's watch it happen. If we could freeze time at one specific instant, the strength and direction of the currents in all 3 coils would combine to create a single magnetic field that points, well, in this case, straight down. Now, let's jump forward just a fraction of a second. The 3 currents have all changed their values a little bit. And look, the combined field has now rotated clockwise. It's pointing in a new direction.
And if we jump forward another moment, the currents shift again. And that resulting field just continues its steady rotation around the circle. And this just keeps on happening, over and over, creating a perfectly smooth, completely invisible magnetic field that spins continuously inside the stator. There are no moving parts here. It's just pure, elegant physics in action. Now, the speed of this invisible field is directly locked to the frequency of the AC power you feed it. And we have a name for this constant rate of rotation. We call it synchronous speed. You could say it's the speed of the magic. Okay, so we've created our invisible, spinning field inside the stator. Awesome. But how does that actually make our unconnected rotor spin? Well, this brings us to the final act of our trick, which I like to call the Great Magnetic Chase. So as the stator's magnetic field is sweeping through space, it slices right across the conductive bars of the rotor, which is just sitting still. Now, there's a basic rule of physics. Whenever a magnetic field moves past a conductor, it generates or induces an electrical current in that conductor. So what's happening is the stator's field is actually turning the rotor into its own temporary electromagnet. So why does that matter? It's because of another fundamental rule of physics called Lenz's law. Basically, it says that nature really doesn't like change. So the current that gets created in the rotor will generate its own magnetic field, and that field is going to be set up to fight against or oppose the very change that created it in the first place. So here's the whole chain of events. The change that the rotor wants to fight is the relative motion between the stator's spinning field and its own stationary bars. The only way for the rotor to oppose this change, to reduce that difference in motion, is for it to start moving. Its newly created magnetic field gets dragged along by the stator's field, pulling the entire rotor with it. It starts spinning to try and catch up, all in an effort to stop the chase.
But here's the final brilliant twist in the story. The rotor can never ever quite reach the same speed as the stator's field. Think about it. If it did catch up, there would be no more relative motion, right? The magnetic field lines wouldn't be cutting across the bars anymore, and the current in the rotor would just disappear. The force would vanish. So for the motor to keep working, the rotor has to always be slipping just a little bit behind the magnetic field that's forever chasing.
So that's the principle, and it's an amazing one. But how does this play out in the real world? Well, while the idea is the same, it turns out that not all rotors are created equal. You actually need different designs for different jobs.
We've been looking at the beautifully simple squirrel cage rotor on the left this whole time. But for some really heavy-duty applications, you need something a bit more complex, like the wound rotor on the right. You can see right away it has its own windings, and this set of slip rings that actually allow for external electrical connections. And this table really lays out the trade-offs perfectly. Your squirrel cage is simple, it's tough as nails, and it's basically maintenance-free. It's perfect for things like fans, pumps, grinders, stuff that just needs to run. The wound rotor, on the other hand, is way more complex and needs upkeep, but its huge advantage is incredibly high starting torque. And that's absolutely essential for things like cranes, hoists, and elevators that have to move enormous loads from a dead stop.
And that really bigs us back to the genius of this design. I mean, think about it. There are no brushes or contacts that can wear out. The main moving part is about as simple as it gets. It starts itself without any complicated electronics, and it's just brutally effective and reliable. It's this beautiful combination of simplicity and power that has made it the undisputed workhorse of our entire industrial world.
The inventor, the great Nikola Tesla, actually considered the rotating magnetic field to be one of his single most important discoveries. It's just this perfect example of taking an invisible force of nature and cleverly harnessing it to do useful work. And that kind of leaves us with a final thought, doesn't it? What other invisible forces are out there shaping our world, just waiting for us to understand them?